Hello guys, welcome back to my channel Gamma Die Gamma. So I know it's been a long break. I completed Black Pen Red Pen's challenge. So I thought I would take a break because university had started and everything. It turns out there were some problems people had with a certain concept, and I felt like I should do a video on it because not all videos on this channel are about mathematical rigor or solving a mathematical problem that hasn't been solved anywhere on YouTube. It's also about providing intuition and explaining the concepts, the theory behind certain ideas properly. So let's get started. So the concept we're going to discuss is convolution. And let me start off with a good analogy, a good example. Assuming you have some ball, you drop it from a fixed height on the ground, and when you do that, it sort of it displaces, and we're restricting the motion to one dimension. It goes, say, some a units, like either to the left or to the right of the point that's directly below the trajectory of the ball. Okay, and let's talk about the probabilities of this ball, say, ending at like some position A. We call that the probability function f of A. Now, if we sort of change the height or maybe keep the same height, but we drop another ball again onto the same setup and see how much it displaces. So how much it displaces by this extra amount. So in this case, if it displaces by A, how much does it go beyond A? See, assuming it goes like B units beyond A. Make note of that, and then the sort of the probability distribution function g of B for that position. Okay, what if I say that A and B, or like the total distance traveled, should be fixed? So what if I say A plus B is C, where C is some constant? So we're fixing the total sort of distance the ball can travel the second time. And now the thing is, okay, how many say C is 3. How many different ways are there to sum to 3? That's a question of partition theory if you think about it. But one way of doing that is, say, A is equal to 2 and B is 1. So it travels 2 units and then 1 extra unit the second time, or 0 units the first time. It just like drops vertically down, and all the 3 units the second time. Well, if we want to find the probability of both these things happening, we have to take a product, right? Because that, if you remember some probability of 2 events happening, we want F to happen and G to happen. So we need to take a product. But the thing is, there's so many different outcomes. Like one outcome is A is 2, B is 1. Other outcome is A is 0, B is 3. Or A is 1, B is 2, A is 3, B is 0. So there's like, I think, 4 outcomes that are possible for this setup. So to basically find the total probability, what we need to do is take a sum of these products. So F0, G3, F1, G2, F2, G1, and so on. And since we're doing this, what we can express this as a sum such that A plus B is always equal to C. So we have to sum A and B to C always. F of A times G of B. Okay, another way of doing this, because see, this summation index is a little messy, is saying that B is C minus A. So we have F of A, G of C minus A, and the advantage of that is, since C was fixed, we only need to sum over A. So A in this case, since it's like a discrete thing, goes from, say, 0 to C. And this precisely is the definition of the discrete convolution of f and g evaluated at c, so that the constant that you fix becomes the sort of the input variable for the convolution. Okay, this is the discrete version of what's going on. Let me give you a better way of visualizing what's going on. Okay, so I would like to represent this by like a diagram. So ball is dropped. We have like possible like scenarios here. So this is like for f of a or whatever, the first drop. And for the second drop, I'm going to represent the probability in a similar way, using this sort of like a branched out diagram here. I apologize for the bad drawing. Just bear with me. Okay, so if we say f of a, which means we're like taking say a here, and this c is fixed. The c is basically the distance from this center to this center. We're keeping that fixed for one sort of evaluation. And then we're summing from a, and then here we have c minus a. So here we have sort of this part here, c minus a. Okay, and when I'm summing, I'm also taking into consideration these intermediate values, because the sum went from 0 to c. So I'm taking this guy, I'm taking this guy, and since our a ends here, we stop there. And then for the bottom guy, we're taking like stuff that's going from say when a equals 0, we have c. So from here, we're going in the reverse direction, and then we're ending here in this point. So it's pretty shabby, but just bear with me. And we only care about what the things that are sort of overlapping. So I drew a small here. If a is like here, like this long, then like the overlapped cases, which I represented by these like shaded like circles. They're like this and this, this and this. And since we're summing, we also care about these intermittent values, because if we just had point A, then we just would care about the last terminal points, but we don't. We care about these. And the thing is, you can see by varying C how many of these overlaps happen. So assume C is like 0, which means this center is facing this center. So you have something like this, like they're like completely aligned with each other. And then if we count the overlaps, well, all of them overlap. So this is like the maximum case. So the max value of the convolution is when I believe C equals 0. So it's like going from, you start from here, right? You think of like moving this C, like it's like a free parameter. So if like C is like negative, well, it won't be negative. Usually, I mean, if you want to think, maybe, okay, fine, let's think it's negative, which means like C is like here, like this. Then, you know, when it's like close enough, this terminal guy and this Y will match, so you get 1. And then when it gets closer, this sort of second last and last match with the first and second, as C becomes tends towards 0. And well, this increases until you reach 0, where you get like the maximum, and then it again decreases. So you get sort of like something like this in terms of like the convolution value. Okay, so this is sort of like the overlap kind of representation of what is going on. And since this is a function, you know, it's a valid question to ask what happens when we vary C, because that's the input of this convolution function. Well, you can think of convolution as sort of the polynomial formula, the binomial expansion formula. Forget these factorials, they're not important. But look at these indices. So a to the n, b to the, a to the n minus k, and b to the k. So you see that all of these always add to n, because you add all the powers, n minus k plus k, you always get n. That's sort of what's going on here, because you add the arguments of each of these functions, you always end up with c, even when c is changing and even when we're summing. See, that's why the sum is over c, because we can't exceed c here. We can't exceed c for this, because this will be 0. This g is basically going in the reverse. As I said, it's sort of, because since we're counting like this way, right towards the right for f, we're counting like the reverse for g to check the overlap. This might not be a little helpful. I mean, you might just say, oh, whatever, this is just some procedure going on here. But a direct example of discrete convolution is the Cauchy product of series formula. If you have two series, an and bn, infinite series, you can like do a product over them, if you can write them like this. So notice this second term here, and then these guys, you notice they add to n, and this guy is sort of like this convolution. So there's like a convolution going on between the coefficients here. So we're summing like a regular infinite series outside, but inside we're also doing a convolution, because it's like a product of series procedure. Okay, whatever, you might again not really care about this. Let me give you a better analogy. We had the function f of a, g of c minus a, right? And then we are summing it over. Well, think of this as like f. So assume you're like shuffling cards. So for shuffling cards, you have like 2 decks, right? And what you do when you're shuffling is you take like a few cards from the first and follow, and sort of, separate them out. So you take 2 cards and then you take like, say, an arbitrary number again, say like 3 cards this time from this deck, and sort of put them on each other. Now, when I take, so say 2 cards are successive cards and these are successive cards, or what you can do is you can take 1 card from here and like 4 cards from here. And again, if I say that like at each time you can like the cards, the number of cards you take, the total number of cards you take from both the decks, they should add up to 5. Then, and you have also the choice of not taking any cards from this deck, which means you only take 5 from this, or you can do 4 1, 2 3, 3 2, 1 4. So think of convolution that way. Think of it as a signal mixing, because when we're going to apply convolution, we're going to apply it to the Fourier transform specifically. This is just the discrete case. For continuous case, we will no longer have integer values in the summation. We'll have all the intermittent values, because it's a function, so it will take like the real numbers, the irrational numbers, the rational numbers between 2 integers also. So instead of a sum, we're going to have integral from 0 to t d tau f of tau g of t minus tau, and that will be defined as the convolution of f and g over tau, over t, my bad. So this is like the continuous version. So instead of like just like taking 1 2 3, we're fixing it at some like real number, and then we can also take like real values. So this is a more involved version of this, because it's continuous. So when I think of convolution, I'm just thinking of like shuffling cards or shuffling signals. F and g of t are signals varying in time, electrical signals or whatever, whichever type of signals. So we're just shuffling signals this way. Okay, think of it that way. Okay, so there's one useful property actually. Say you take the Fourier transform of the convolution of 2 signals. You get the product of their individual Fourier transforms. Again, you can do this for Laplace as well. I'm showing it for Fourier first. And we will talk about the intuition about this later. So integral from 0 to negative infinity to infinity of we have e to the negative I omega t. This is the definition dt of the Fourier transform, and then integral from minus infinity to infinity f of tau g of t minus tau. This is the convolution formula d tau. You might say, well, there was a 0 to t before. That's because we are assuming that for t less than 0 both of these guys are 0, and that makes sense because if you consider like the 0 to like negative infinity to infinity case, f of tau and g of t minus tau d tau, well, if you have negative infinity to 0, that on that interval f of tau will be 0, so it's 0, so don't worry about that. Okay, that was for the negative interval. For the positive interval, you can only go from 0 to t, because if you exceed t, the g argument becomes negative and then we run into problems. So t to infinity, g becomes negative and then it's 0, so don't bother. That's why this is equivalent to the original definition of the convolution that we were using. So it's justified to basically switch to this negative infinity and positive infinity. That's useful because I can like interchange these integrals. So now I just have, say, d tau f of tau negative infinity positive infinity dt e to the negative I omega t g of t minus tau. You can do a variable substitution, variable change, and you're going to get, say, du e to the u is t minus tau at I omega u plus tau g of u. Take the tau out, f of tau e to the negative I omega tau negative infinity infinity du e to the negative I omega u g of u. This inside guy is just the Fourier transform, and you can change from like u to t again, it actually doesn't matter. This is just going to be the Fourier transform of g, and this guy will become the Fourier transform of f. So there we go, we have proved this identity. Now what does this actually mean? Well, if you kind of look at it, what this is saying is if you shuffle the signals f and g, you get, or what the Laplace the Fourier transform does is it basically tells you what combinations of the coefficients of those basic e to the what linear combination of this function was in f of t. F of t was composed of how many of these guys. That's what it's telling us. So because it's like a linear combination, in this case an integral, so this gives you a number onto this. This is like the coefficient space, or you can think about like the frequencies domain. So it gives you information of how many of like what was the distribution of like what were these coefficients for these varying exponential factors in each of these, in the breakdown of each of these functions. But so if you mix them, it says that that's equivalent to multiplying the coefficient distribution of each of those functions. So that's a really abstract way of thinking about it, but sort of like mix the signals, but the Fourier transform will like recognize them as the product of like the coefficient space, or the frequencies will get multiplied. If you mix two time signals this way, the frequencies of those of like the base signals of which these guys were composed of, they will sort of get multiplied. This is a like a, you can think of this as a physical phenomenon or a mathematical idea, but this is what this is. This looks like. You can also sort of see that you have a product, take the Fourier transform, like equivalently you get the convolution of the individual Fourier transforms. So it's another property. I won't prove it in this video, but this video was supposed to give an intuition about this. I hope it helped. I urge you to do more reading on this. You can look at the case of the moving square wave. So when when like they overlap, that's when you get like a convolution becomes like a spiked, and when they're perfectly aligned you get this peak, this max value, and then it decreases. So I urge you to look into that. It's on Wikipedia. So yeah, that's it for this video. Please like, share and subscribe to my channel, guys. Recommend to your friends, spread the word of gamma diagram in the math community, and please stay home, stay safe, keep doing math. Peace out.